This project explores flow path resistance in heterogeneous porous media as a graph theory problem. Before jumping in, I want to thank my advisor and collaborators for the immense help on this work, and I also want to acknowledge the funding sources, the ACS Petroleum Research Fund, NSF, and the AXA Research Fund. Here, we plot a normalized concentration versus time, where time is represented as pore volumes. This data is from a bromide tracer experiment ran through a sand column. It has a long tail in concentration, which is a signature of anomalous transport and is not captured by the ADE modeled here. But why? Here is the ADE, which states that the change in concentration in time is the addition of the advective and dispersive term. Both of these terms use a representative average velocity value, and this value comes from Darcy's law that describes the system's flow and states that the system's velocity is equivalent to the permeability times the hydraulic gradient. The inaccuracy of the ADE predictions come from this average velocity value, which fails to predict a system's flow complexity and leads to incomplete predictions in early breakthrough and long-tailed concentrations, as shown here. Improving the predictive capability of a transport model requires that the full range of flow heterogeneity be understood and incorporated. In this project, we worked fundamentally with flow at the pore scale. Through this work, we learned where, how, and why complex flows develop at the pore scale. We did so by first characterizing a sample's pore space by its channel geometry and network topology. Then, we predicted the location of a primary flow region using the pore network topology and geometry. Finally, we explained how neighboring channels' structural similarity or order is related to flow channelization. This project used thousands of 2D tomographic slices and recast them into equivalent graphs. Let's consider this example of a binary porous medium where gray is the solid and white is the pore space. We first convert the pore space into its topological skeleton. Then we split that skeleton into nodes and edges, where channels are the edges and channel intersections are the nodes. After identifying the nodes and edges, we recorded the channel geometric information, including the arc length, Euclidean distance, and pore width information, as well as topological information like node degree and neighboring nodes and edges. Direct numerical simulations were performed on each tomographic slice, providing a velocity field. We want to divide this velocity field into regions of fast and slow flow. We first normalize the velocity field by the average sample velocity. Then we classify pixels by comparing their normalized velocity value to some threshold, which we will call the percolation threshold, or PT for short. If the normalized velocity is less than the threshold, it is classified into the stagnant flow region, shown in blue. If the normalized velocity is greater than or equal to the threshold, it is classified into the primary flow region, shown here in white. We initially set this percolation threshold to be at the sample's maximum normalized velocity. For this example, that is 8.7. At first, this classifies the entire pore space into the stagnant flow region. Then we iteratively lower the percolating threshold value until a continuous path of high velocity is formed, connecting the inlet to outlet. This continuous region is shown in red and is called the percolating path. In white are regions that also meet this threshold, but are disconnected from the percolating path and scattered throughout the velocity field. Using this approach, we learned that for this sample, we expect that early breakthrough will occur 1.5 times faster than the average sample velocity, indicated by the 1.5 percolation threshold. Shown here is a histogram of the percolation threshold for each sample in the dataset. We can use the percolation threshold to classify samples into different flow regimes. Let's consider these two velocity fields and divide them into velocity regions using the percolation threshold. The left sample has a lower percolation threshold and has more uniform flow. The right sample has a higher percolation threshold and has more channelized flow. We reduced the pore space to an equivalent graph for more efficient path finding. To find the shortest path through the graph, we first added an ultimate source and target node that connected to all the nodes on the inlet and outlet boundary, respectively. Then we used one or some combination of channel geometric characteristics as the edge weight. Changing the edge weight changes the predicted path, as shown here in different colors for different models. How well an edge weight performs is based on how well the shortest path matches the known primary flow region. To find the best edge weight, we use differential evolution, an evolutionary algorithm. Differential evolution would improve the edge weight by changing what geometric attributes were being incorporated, aiming to increase the match between the predicted path with its known primary flow region, while penalizing for over-parametrization. I want to emphasize that while I have been showing one sample for illustrative purposes, this algorithm was actually optimizing for a dataset with thousands of samples. We found that the best edge weight is arc length over mean width, or L over S. Shown here is a complementary cumulative distribution function, which tells us the probability for a sample to have at least some given accuracy. From these CCDF curves, we can say that our solution, the L over S metric, will more accurately locate primary flow paths relative to our control, the unweighted scheme, which finds the path with the least number of steps across the sample. For example, using the unweighted scheme, half of the samples would have an accuracy of at least 0.6. Comparatively, using the L over S weighting scheme, half of the samples would have an accuracy of at least 0.8. This answers the where primary flow occurs and how to describe it based on structural information. The answer to why paths form at these locations lay in the network's structural organization. First, we took our graph and separated the edges into the primary flow region, shown in red, from those in the stagnant flow region, shown in blue. Note that the edge width is proportional to its L over S value. This created two subnetworks. In each subnetwork, we were interested in how structurally similar or ordered the edges were. Specifically, we explored how similar the L over S metric was between edges within each flow region, which we'll quantify with the symbol R here. Here, we have the R for the stagnant flow region plotted against the R for the primary flow region. Color indicates the percolation threshold. Each data point represents one sample for which we can learn its stagnant flow order, primary flow order, and its percolation threshold. In this plot, most of the data falls below the black 1-to-1 reference line, showing that the order is greater in the primary flow region, and thus primary flow regions tend to be more structurally ordered relative to the stagnant flow region. This indicates that primary flow develops through connected channels with similar L over S values. This contrast increases with percolation threshold, indicating that flow becomes more channelized when the primary flow subnetwork is more ordered than the stagnant flow subnetwork. In this research, we quantitatively characterized flow channelization with the percolation threshold and found that primary flow develops through the shortest, in terms of the L over S metric, pathway of interconnected channels, and that the subnetworks of primary flow are more ordered than the stagnant flow, and that contrast increases with flow channelization. Again, I want to thank my advisor, collaborators, and funding sources. Thank you for your attention.